Good afternoon, everyone. Thank you all for coming. My name is Rob, and we're here today to share with you what we did for the past year in this RoboTeam Twente, and what we basically spent the whole year doing. But before I want to do that, I want to go a bit back to a bit more than 3 years ago, where a group of ambitious students here at the UT decided to build soccer robots. People interested in mechanics, electronics, software, AI, they decided to come together and found what is called the RoboTeam Twente. And within a year, they managed to build this robot over here. And especially looking back at what we have been doing this year, having a good foundation, I can still only really respect what they managed to pull off in 1 year. Not only did they manage to eventually qualify themselves for the RoboCup Small Size League, they also managed to put a great foundation to what two teams still build upon. 1 year after, the second generation of our team built upon this success. They built an entire new robot, put a lot of effort into this, and in a bit you will also see that this robot design still forms the basis of our current robot design. They managed to qualify for the A division in the RoboCup in Montreal, Canada, where they got the 7th place. And then of course, after them, there's us. And before I would like to share with you our robot and what it can do, I would first like to invite our guest speaker, Edwin, who did robot soccer a few years ago, 11 right now. So please, Edwin.
Okay, thank you so much, and thanks for this invitation. First presentation ever to pull off on socks. Yeah, let me add a little bit of legacy and even further depth and further history to your 3 years of qualification, your 3 years of prior history presented here. Because indeed our university has been part of RoboCup, has been part of robot soccer for a little bit longer than that. So let me tell you my personal story and personal involvement, because indeed at some point in time I could have been qualified as a professional soccer player, in the sense that university was paying me and I was playing robo soccer. So if I skip the robot quickly enough, it's like being a professional soccer player. Yeah, right. Okay, this is what I do. I'm an electrical engineer by trade. I'm trained and educated here at Twente University, electrical engineering, specializing in mechatronics. So this is me in my natural habitat. And currently I work at the Robotics and Mechatronics group here at Twente University, where I teach mainly in a program called Creative Technology, but do research or contribute to research, which has much more to do with inspection, maintenance, robots for care, real functional robot technology in a way. However, I've been fascinated by things that move around, things that can drive around for already a pretty long time. So digging a little bit back, my first sort of encounter with tiny moving robots that have to play a game was my bachelor's assignment, already 2003, sorry, it's really a trip down memory lane. But in 2003 I contributed to this project where we already started designing a small team or a small group, at least a group of two, a team of 2 tiny robots being able or being capable of playing games. I like this really much. Not just from the engineering point of view, I also really liked at the time the idea of gamification. There were creative design competitions at the time being held between the technical universities in the Netherlands. And now if you ever wondered why there is this weird goldenish trophy in one of the display cabinets in the Zilverling building here, it's actually this trophy that our university won during one of the first creative design competitions. Yeah. Well, it was a very, very nice competition. You can see it as a crude form or a precursor to something like RoboSoccer. You have 1 week, small team, 1 design challenge. You have to build a robot. Usually these are tiny moving robots that have to fulfill a task. In this case, we bit the shit out of Delft in capturing balloons. Really proud of this. This case, let's keep silent. We took the idea a little bit further. because there's, of course, much fun and much things to learn if you participate in these competitions yourself. However, it's even much more fun to organize these competitions for younger people. So just like the RoboTeam is doing with the Make a Block education, what you saw in the movie, this was, you could say, kind of precursor to that. In this case, we invented a game where participants in the summer school had to build a robot that had to capture small, annoyingly programmed yellow Lego robots and collect as many of them as possible, while doing sometimes even destructive versions of that. Well, anyway, having said that, I was allowed to graduate here, and I was allowed to graduate on this project, of which I was apparently really happy. This is a walking robot, walking on the amount of energy that you can store in 18 penlight batteries. For humanoid robots, that's pretty efficient. Downside of this robot, or the only thing that this robot can do, is walk. And walk, well, yeah, just walk. Or at least say, let's say, walk as in falling forward. Or walk as in continue to fall forward. So the thing is, like, if you want to minimize the amount of energy that you use while walking, you simply let your weight drop on the next foot, and then if you're quickly enough with the next foot, you keep on falling, and as you keep on falling, that's like walking. And the Alicia Keys songs apparently, but okay. So having said that, the amount, or hang on, the quality of a robot like this, there's a very, very important key performance indicator, or very important quality indicator here, which is not so much the amount of batteries that the robot is using, it's not so much the walking speed that it can achieve, but the quality of this robot is measured by the amount of distance that the creator of said robot dares to make when this robot is walking. Here you can see this criterion set of roughly 1 meter, and not for nothing. Okay, I was allowed to continue this style of work here. Did a PhD project on a pipe inspection robot. But before I had that lovely opportunity, indeed, our university got together with the 3 other technical universities after the Createch design competition. We settled our differences, and they teamed up with Delft and Eindhoven to take part in the RoboTeam competition at the time, 2008, in China, which was huge, as things are, they tend to be in China. And this was the robot, or at least this was the artist's impression of the robot, Tulip. And we were about to participate in the main, not the team, or I think the team-size humanoid league. So you have right now the small-size humanoid leagues, small robots. You have the stand-up platform, like the nano robots. This was just mainly designed at building full-size humanoid robots. So we participated. Transportation at the time was rather primitive. Here you see our robot ready to go to Delft from Twente. You see the Hogekamp parking lot and my Volkswagen T3. We did not invent flight cases by then. Here you see our lovely contribution in the pit stop in China. And here you see this robot, our humanoid robot, our 4TU, 3TU robot, no, not that one, that's our contestant. You see in this movie our robot in action. This is the moment of glory, the first moment of glory of the robot Tulip. Like collaborative effort of the 3 technical universities in the Netherlands. Of course it always takes a little time. And you can imagine the amount of tension that we had standing there behind our robot in the goalpost. And here comes Martijn Wisse, currently director of the Biorobotics Lab in Delft. There you see our robot. And the thing that it does, well, it tracks the ball, or it moves its head randomly. I think it's tracking the ball. It should be tracking the ball. And now Team Osaka, the Japanese guys, make themselves ready for the final kick. Everybody's holding their breath. Imagine the amount of joy we were overjoyed because, well, at that time it was already pretty hard to make sure that this robot remained standing, let alone putting up his leg or whatever. So the next year we also participated in grass. You see Windel, one of our master students, taking part in the foot race, and he's hardly touching the robot, almost not at all. But okay. Thing that I want to add to that. It was a tremendous amount of fun to participate in these competitions, and I think on a practical practical level, on a social level, and on the kind of skills that you need as an engineer to work in a team, and to really to be ready for an engineer for the real world, these competitions, they are invaluable. So this is really learning for the real world. During this competition, that's where your real education takes place. Another point, what I thought on hindsight is really interesting, pick your own battles. Because, of course, it's a competition, and the rules, the play field, all the rules, the referees, etc. is laid out by an organization. However, you, as a team, have a tremendous amount of freedom to look for the edges, to see where you can do the innovations and where you can make a difference. So, I think prior to our competition, there was not such a thing as a foot race. But apparently we designed a robot that was very good in walking and not something else. So, okay, the judges and referees said, okay, let's have a foot race competition then, which we won. Haha, yeah. So then again, yeah, this is where the real learning takes place, but also make sure you find the edges where you can actually pick your own battle. And with that, I would like to give the floor back and hopefully enjoy the presentation of the new robot. So thank you very much.
So much, Edwin, and we have a little small something for you.
Thank you so much.
Thank you. Yeah, so continuing from there. Before we reveal our new robot, I would briefly want to take you over what we've been doing for the past year. Starting, of course, in September with a group of 15 students ready to build a robot soccer team, improve a robot soccer team. We were sure what we were doing, but we also still had a big challenge ahead of us. But already 2 weeks after, we went to the technology base, which is right here at Twente Airport, because next to innovating our robots, next to sitting just in our office, testing and programming everything, we want to share what we do with other people. So here you see us with our demo field, with just a few controllers, let people control our robots, play against our AI, and just show people how they work, and just inspire people to like technology, to like AI, to like robotics. And the same we did a month later in the Innovation Expo in Rotterdam, where a lot of participants just passed by just to ask questions. And there you see simple questions, easy questions, questions ranging from how do you exactly make your robots do stuff, to far actually more difficult questions like, why does your robot have a mustache? All these questions we get here, and actually the whole AI stuff is sometimes more easy to explain than why we decided to give the robot a mustache. And in December, this was the first time where we shared with you our plans. What was it that we were going to do? How are we going to improve something that two teams already worked hard on? And what were we going to do to hopefully win, hopefully have a good result at the RoboCup. And in a bit we'll show you what that is. But then I think the biggest challenge, and I can speak on behalf of all of us, was our qualification. The moment where we had to prove to the rest of the RoboCup society that we are ready to not only participate in the RoboCup, but also in the A division, the highest division of the small-sized league. This would of course be a challenge, but because we do want to stay on top of innovation, we did decide to try to compete with the best of the best. So we worked really hard that week, and yeah, if that worked out, you will see in a bit. After this, we went to Embedded World with our main sponsor, Xperia. Here we showed at the Embedded World Conference not only how Xperia components, but also just the components of all of our sponsors help us to make an even better robot. Because with all of this help, we couldn't make the robots that we have right now. And then, on the 4th of March, the good news finally came in. We did manage to qualify for the A division. This was of course good news, because this is what we aimed for, but at this moment we also knew that we still had a lot to do to work towards the RoboCup. And next to just innovating, as I already mentioned, we also want to share what we do with others, which is why we collaborated with Kiwi Electronics to get 10 MBots, which are basically educational robots, not only much easier for kids to play with, but also less expensive. And here we just give workshops to show people how fun robotics is, And well, to show them how relatively easy maybe it is to let a robot do simple stuff like driving around, like following a line. And after that we went to RoboTeam Twente, as our name already suggests, RoboTeam Twente. We have some connection with them. But also for a robot soccer team, we have relatively little people that know a lot about soccer. So we thought this should probably change. We should have some advice for people that know what they're doing. So we went here. And on one hand, this is a bit different because, as you can imagine, human soccer and this size robot soccer is quite different. But especially on defensive and midfield point of view, they actually managed to give us a lot of input and just help us a bit with the tactics that we could be implementing in the RoboCup. And then the biggest event we pulled off this year are practice tournaments. Of course we can prepare for the RoboCup in a lot of different ways by just practicing in our office on this field. But we wanted to practice a little bit more, so we invited 2 German teams, Mannheim and Air Force, to come over here to Enschede, to the design lab here at the university, to play against us. These are 2 teams, currently 2nd and 4th in the competition, that we, on one hand, knew we probably wouldn't win from, but it would still be a really good learning experience. Our results weren't too great, but one of the main reasons that we wanted to put on this competition is to find bugs, errors in our system that we would have otherwise maybe only have found out about at the RoboCup itself. So this was a good practice moment to test all of this. And now here today we are at a reveal presentation about to reveal our new robot that we will, in a bit more than 2 weeks now, fly to Sydney to participate in the RoboCup 2019. As I mentioned, next to innovating, next to inspiring, next to education, we actually want to put even more focus on education, while we also have some students from outside our team with us. We've had a design assignment with computer science and 2 bachelor assignments running with us. One on the topic of machine learning and one on the topic of industrial design. And on the second topic I would like to invite Daan to tell us something about what he did with us. You probably have already seen his field outside. So Daan?
Yeah, thank you. Hi, so I'm Daan, student of industrial engineering, and for my bachelor assignment I was looking for an assignment in which I could create something and will meet the requirements to fulfill the assignment. So, as Rob mentioned, there are a lot of places where they want to show, where the robot team wants to show the capabilities of the robots, but to show the capabilities of the robots you obviously need a field. And as you could imagine, not everywhere they go there is a space like this to set up a field with this size. So they have a smaller side field, and they can set it up at all the places they go to show the robot capabilities. They wanted this field, so they could set up this assignment, and it's to design and produce a portable soccer field that ensures clear visibility of the color markers on the robots. The robots each have individual color marker patterns that are being recognized through the camera by a computer, and those color patterns have to be seen clearly in order to be recognized. As you can see, the old field, this was the version of the demonstration field before mine, and it's just a flat field which doesn't support anything for the illumination of the field, which has to be constant. So it worked, but there were some lags that I needed to improve. And as you can see as well in the picture on the bottom, the field material got fuzzy after a while, so it got loose and stuck in the wheels of the robot, so that was another design problem. Thereby, this field is too big, it consists out of 4 parts, it's too big to transport in a car, which was one of the other requirements for this assignment. So, first I had to do a lot of analyzing. How does the system work? Why is the system so sensible for different colors and irregular illumination? After that I had to do a lot of testing. What material can be used for the field, and how to create stable illumination on the field. So with the testing, there were a lot of things that I couldn't do myself, and I thought of the test myself. But I'm not a programmer or a software people, one of the software people. So I needed some help from the RoboTeam, and they supported me in everything that I couldn't do myself. So I set up the test, or I set up the entire, what I wanted to do, and they helped me through it. So for example, here in the video, in the left corner, you can see that I put up a small test setting to test different field materials, potential field materials, and so that I could select the right one. And they helped me with driving the robots, etc. In the picture next to it, in the middle, you can see that I made a setup to test different illumination settings, and when the system crashes and when it doesn't, so that I get information for the field that I was going to make. I had to do a lot of sketching. This is just the top of the iceberg, and with that I created multiple ideas, and together with the RoboTeam we selected the best ones with my advice and their opinion and experience, and so we could combine everything into one design, which I built. I did a lot of laser cutting here at the university, and I ordered materials and everything. The building I did mostly myself, but then it came to testing. And one of the biggest requirements was that it needed to be transported by car. So we tested it, and this car is available for the RoboTeam during this year. So this was the car that the field needs to fit in, and as you can see, it fits. So I'm very glad that it does. And you might have seen it, it's here outside. This is the field. The bar on top is a light bar, which ensures a good illumination of the field. And I used a fabric that's used for outdoor furniture. So it's used to, it's a really strong material. And they can just put this field up in a few minutes on location. So that's my final design. So you can do a bachelor assignment at the RoboTeam, and you really get a lot of support where you need it, and they let you free to do, to use your own experience and advices and insights to create the best you can do.
And then, without no further ado, I would like to present to you our new robot.
Take my hand and come with me because you look so fine that I really want to make you mine. I say you look so fine that I really want to make you mine. 4, 5, 6, come on and get your kicks. Now you don't need the money when you look like that, do you, honey? Big black boots, long brown hair. She's so sweet with her get back stare. Well, I could see you home with me, but you were with another man, yeah. I know we ain't got much to say before I let you get away, yeah. I said, are you gonna be my girl?
Of course, just what a robot looks like and a bit of how it drives. But to tell you a bit more about what it actually can do and how it works from the inside, I would like to invite Lucas to the stage to tell you a bit more.
Thank you, Rob. So I'm very proud to talk to you about our new system We designed completely new robots this year. We have a lot of new improvements this year, and our team has worked so hard. Sometimes we had to work through weekends, we had to work evenings, and it's just because we love doing this work. And I'm very proud that today I can show everything that we have done this year. So, one of the questions I often would get when I try to explain how the RoboTeam system works to my family is, do these robots think for themselves? Do they actually have a brain or something? Well, they definitely don't have a brain. Because it's sometimes a little bit difficult for people to understand, I would like to say it for once and for all, at least for this afternoon, how the system is working. So, I'm standing on the field. I've put on my nice socks for today. We wear our socks because there shouldn't be any dirt on the field, of course. And on this field, we play our robots are playing. But these robots have to be controlled by a computer. And the computer, it's standing over there, is the brain. So our robots, they just receive commands from the computer. And a command can be an angle, or a velocity, or kick now, or do a chip, or turn around. Well, that's actually not a command, it's like go to angle 180. So the computer is the brain. The computer does make all the decisions, and for every robot, the computer knows what that robot is going to do and lets that robot know. For that, it uses a base station. You cannot really see it clearly. It's a large light on top of the computer. And the base station is connected to a wireless connection with the robot. And the computer wouldn't be doing a lot if there weren't any cameras above the field. So we hung up 2 cameras today, and these cameras are registering everything that's happening on the field. So the camera has a topside view of this field, and because we have 2 cameras, we actually need to combine the data streams of both cameras. And these data streams get processed a lot, and then our computer can make decisions on these data streams. When these decisions are made, the commands are sent to the robot. The robots start moving, start doing things, and that gets registered again by the cameras. And then we have a full circle. Let's start with the robots. This year we have a new generation of robots. Although its architecture is mainly based on the same architecture of last year. So a large part of the structure remained the same, although we did some significant upgrades. Let's quickly see the first upgrade. One of the things we had last year is the Geneva drive. The Geneva drive allows us to shoot at an angle. And shooting at an angle is a huge advantage, because the cameras are not able to see in which direction we are going to kick. They just see the direction in which the robot itself is oriented, but they don't see the direction in which it is kicking because of our Geneva drive. We can kick with a deviation of 20 degrees to both sides, so there is a 40-degree difference between the outer states. Next to that, we have a ball sensor. And the ball sensor allows the robots to know that it has the ball. This is a huge advantage over what is usually done. Usually people see the ball with the cameras, but sometimes the robot is blocking the camera from seeing the ball. Sometimes when the robot has the ball, the camera cannot see the ball anymore, which is a problem, of course. Also, there is a latency in the camera, in the data stream of the camera. This latency can run up to 50 milliseconds. If you are 50 milliseconds late in knowing you have the ball, you could have missed a nice shot. And 50 milliseconds doesn't sound like much, but our robots can go pretty fast, and you could have moved 60 centimeters in that time. This is an example of how quickly we can shoot with the new ball sensor. It's pretty fast, the image is looping, yes. So we instantly kick. With our system, we can say to a robot that whenever you have the ball, kick. So there is not any delay in, an insignificant amount of delay in knowing you have the ball and shooting it. and the computer takes care that the robot has a nice angle and is, for example, angled at another robot for a pass or at the opponent's goal, preferably. So that's the ball sensor, and now let's go on to the top board. And I just said that the robot didn't have any brains, but if I were to say it does have any brains, then the top board would be the brains of the robot. At the top board, we do all kinds of logic. Motor control happens here. We have all kinds of sensor inputs, outputs, which we have to register, and it all comes together on here, on this robot. This year we even have a buzzer on there, so our robots can make little sounds when something is wrong or when we boot it up. Well, I'd like to show you the quick details of our new top board. We made some major improvements, and the first thing I would like to talk about is the communication. We learned from last year. Last year at the RoboCup, we had significant problems with the communication. One of the team members had to hold the base station in his hand and hang above the field to make sure that the robots are still connected. This was occurring because there was so much interference during the RoboCup. There were all these teams playing robot soccer and they were all on the same frequency. So because of that, there was so much noise that our own signal couldn't get through the noise. And a lot of our robots were unfortunately standing still. So this year we had to improve our communication by a lot. So let's take a quick look. Last year we could transmit signals at a decibel per milliwatt. That's the range in which you call it. It could transmit at 0 dBm. And it could receive packets up until minus 85 dBm. This year we managed to increase that to a transmission of 12.5 dBm and a receiving of minus 100 dBm. This maybe doesn't sound like much of an improvement, but we are talking about the logarithmic scale here. And that has some serious consequences. If I were to say what the range of our communication would be in an ideal situation, then the previous communication would reach 60 meters. That would be without any obstacles in between and without reflection from the ground. With our new communication, we are able to go to 500 meters in the same situation with the same levels of noise. So our communication has improved a lot, and currently in practice we could sit like 200 meters. We could sit in the Bastille and still transmit messages to our robots. Another improvement of our robots are the motor drivers. Motor drivers are very important and we really wanted to improve them this year. Motor drivers are responsible that the robot can drive fast, and they are also responsible that the robot can be very accurate. And well, we like our robots driving fast and we like our robots being accurate. So we have made some significant improvements over here. One of the improvements we made is the maximum velocity. The previous maximum velocity was 80 kilometers an hour. That's nice, that's a very nice speed already, but we wanted more. This year we doubled the power output of our motor drivers, and the output current is 3 amps, and that's a lot for our robots, by the way. And we managed to increase our maximum velocity to 7.3 meters a second, which is more than 26 kilometers an hour. Obviously, this field isn't that large, so we are not able to reach this maximum velocity during a game. Especially in soccer, just like normal soccer. In robot soccer you have to accelerate and decelerate a lot. So most of the time either you're standing still or you're intercepting, but it's constantly braking and accelerating, decelerating again. So our robots also have to withstand that. But by constantly accelerating and decelerating, there is one major problem. Because the energy while braking has to go somewhere, and that goes into heat. So we realized there was a small problem. Our motor drivers would get pretty hot, but now we have upgraded them and they can now withstand 120 degrees of temperature. So yeah, after a robot has played for a while, you shouldn't touch the motor drivers. And also, we added some holes in the caps of our robots such that we would have a nice airflow while the robot is driving. Then we have the X-Sense chip. The X-Sense chip is an accelerometer and a gyroscope in one, and we heavily rely on this year. The X-Sense chip was on there already, but we have extended the use a lot. We use the X-Sense chip for control on the robot. What does that mean? A robot has to turn to a specific angle, but how does that robot itself know what angle it has? We have to tell it somehow, right? So we send that data with the camera to the robot, and then we say to the robot, hey, this is your angle. So if you want to turn 90 degrees, then you have to, you want to turn to, for example, 90 degrees, then the robot knows about this. Unfortunately, the cameras have a latency of approximately 50 milliseconds. So the data would always be late. But with this chip on our robot, we can actually already know beforehand what our new angle will be. So we can actually let the robot itself estimate its current angle and its current velocity. And in this way, we have much better control of what our robot is doing. This improves our accuracy by over 50% at low speeds. Well, with these new motor drivers and this X-Sense chip, we also added another great feature to our robots. Because by braking very fast, we could make our robots do backflips. So we already had it imagined. We would go to the RoboCup, and every time we scored a goal, we would let all our robots do a backflip at the same time. Well, actually, if you look at this from a control point of view, this is not a very good thing to do. It's also pretty bad for the robots. So we had to find a solution for this. One of the solutions I really like, we all really like the solution we came up with, is we decided to change the bottom part of our robot. And we replaced the whole bottom part. We replaced all wheel mounts and gears with metal wheel mounts and gears. The gears are now, we were previously made of foam, which is some kind of plastic. But now they are made from brass. And the gears are way better in interlocking with each other. And because there is, they don't wear down that much during play. And sometimes we really abuse these wheels. So this was a nice improvement. And also the weight, has, the center of mass has been going down physically. So there is less of a chance to do a backflip. And because of this change, we can also decelerate faster. And braking fast is actually very useful during robot soccer. Yeah, so this was about the robots, and now I would like to talk a little bit more about the computer part, about the brain part. And this year in our team, we had quite a lot of software developers. So we wanted to do something big. We decided that we would go to the drawing table and came up with a list of personal requirements. And one of the things we really wanted was an insightful system. We wanted to know what was going on inside a robot. Sometimes a robot would behave in a very weird way, and we didn't know why. So we want to know what the robot is doing, why it is doing what it is doing, and if things go wrong, we want to know what it's trying to do and why it's going wrong. So we wanted to have a lot of insight. So that would already indicate a major upgrade in our system. Also, we wanted the system to be modular. And by adding modularity, we would actually be able to push updates way easier. If we are at a RoboCup, we have to be able to adapt fast. If there is a team and we have a mistake somewhere in our code, we want to be able to swap in new code in a matter of seconds, because we only have a timeout and we only have a very short amount of time to make a fix. So we designed, we really wanted to design a system that would be able to support this. Furthermore, which is maybe the most important thing in robot soccer, we wanted a system that would be very reliable. Reliability is really important because there are so many factors that can be causing problems in your system. For example, the cameras have to register everything and it has to be processed and filtered, and then the decision-making process. Again, that's so much more, and there are so many places where things can go wrong. So we really wanted to focus on reliability in our system, and we really wanted to think through all of the things that could go wrong. So, with these changes in mind, we decided to do a full rewrite of the software of RoboTeam Twente. This was a major effort, and we put lots and lots and lots of time in it. And I'm not going to be very subtle about the name. We all think it would be a very fitting name. We call it RoboTeam AI. And RoboTeam AI has all the features we need. So it has this modularity which we wanted. We can exchange code within a second, 200 milliseconds to be exact. And we can visualize everything the robots are doing. And we can log things. We have all kinds of beautiful new things. We have this new interface. We have completely built this ourselves, especially for our robots, for our system. And when things would go wrong, we can see all the details. For example, how fast our robots have been driving, absolute velocities, the vision and goal, how dangerous a robot is. All those things, we have insights in this now. And about modules. And we made some very nice modules in our data. And I would like to talk about our most important ones. Because something every robot has to do in robot soccer is driving around. So we decided that we actually wanted one very advanced module for driving around, because every robot has to drive around. So we started with this module and we thought, let's make this thing very advanced, because we want to drive fast and we want to drive safe. So let's take a look at a half field and let me explain you how our new algorithm works for pathfinding. Imagine this is the current situation in the field. We are playing with the yellow robots, and one of our robots has the ball. It's a very good thing. Unfortunately, there are also two blue robots blocking our vision to the goal, so we cannot really score immediately. We also have another robot in the field, but it cannot really go in. So, it cannot really do anything with the ball, I mean, but it can go in. So we want to let it drive to the green cross to have a very tactical position. It has very nice goal vision, and it also can hopefully receive a pass from the robot that currently has the ball. Well, our algorithm is so advanced, it just tries to go there in a straight line. Beautiful. Unfortunately, it's not possible, because we intersect with the defense area. And in robot soccer, you're not allowed to enter these areas. So, we have to avoid the defense area. Well, we just know that it's a defense area, so let's pick two other points to drive there first. Maybe we can go next to the defense area already in a safe way. So, let's pick two other points, and let's go there in a safe, straight way. Unfortunately, there are two robots blocking that field, so we cannot go there. So we have to try something else. But we know a robot is blocking our side, it's blocking our line. So we go to the robot closest to the end destination, and we pick 2 points next to that robot. Well, I think most of you already see where this is going. This is some very nice recursion over here. And we try straight lines to these points again. Oh, yeah, there it is. And then we have a safe path. Yeah, click it. Yes. We do some curve fitting over it. And this curve is highly exaggerated for presentation purposes. But this will be the final path for the robot, and we know it's a safe path, which we can drive over fast and safe. But our position control has way more. I just explained it like the robots wouldn't move, but we have a prediction-based model. So it actually tries to estimate the future. It tries to see all the velocities of other robots, and it takes that into account. And therefore, what I forgot to mention, it's also super fast. Every calculation is finished in a matter of milliseconds. And that's very important, because more performance is good for us. The faster we can give commands to the robots, the better our control actually is, and the less time opponents have to respond to it. Next, I would like to talk about our BAM ball handling controller. Handling the ball is very, very difficult because the ball, there are all kinds of physics in the real world, and you have to take them into account. This year, we have a completely new system for it. So imagine one of the blue robots is trying to pass to his friend, the other blue robot, but it fails. This happens quite often. This is the opponent, by the way, not us. We always pass. Brilliant. And imagine it fails. We have a nice yellow robot, pretty close. When it realizes that it fails to pass, we are now able to actually catch the ball. So when we realize that the ball is going in a with quite some velocity, it's going outside of the field, we are able to catch it. And last but not least, I would like to talk about the shot controller. Remember the Geneva drive I talked about, or the ball sensor I talked about? We over-engineered those things to the max, and we tried to make so much use of the Geneva drive and the ball sensor. And we wanted to make a general module for all robots to use, such that when we would have worked this out, everything in our whole system was able to use Geneva shots and the ball sensor. So imagine the yellow robot wants to go to the ball to pass to the other yellow robot. This is how we previously do it. But we have a Geneva drive, so we can do better than this, right? We can make a way shorter path, and while driving that path, rotate our kicker to instantly make a kick. This has two advantages. The first advantage, we are faster to the ball and we can kick faster. The other advantage is we use a Geneva, so it's very unpredictable for other teams to see what we are actually doing. And every robot uses it. Well, sometimes, unfortunately, it happens that a robot breaks. For example, if it collides with another robot. There are especially some teams from Iran, we are warned by the journalists at the practice tournament. They said they will collide with you. You can be sure about that. So we had to have some safety measures, and we actually built it in such a way that we can indicate that the robot has a broken component, and the software will handle it. So if the Geneva drive is broken, which hopefully does not happen, it hasn't happened yet with the new ones, we actually can compensate for it by just always shooting in a straight way. Or if the ball sensor is not working, then we can always compensate for it by just prediction with camera, and we have some very fancy models for that. That was what I just said actually. And I talked about the robots, I talked about the computer, and last but not least I would like to talk about the cameras. And the cameras are very important for us, because without the cameras we couldn't do a thing. And this was our previous vision from the camera. This was what we would get, and this was what we would have to make decision. The yellow lines, the white lines are actually the measured velocities of the robot. And these deviate a lot because there's so much noise. So when trying to predict what a robot would be doing is very difficult because its velocity is going all over the place. You cannot make a decision based on that. And also its position, it's deviating by, this is about a deviation of 5 centimeters. That's not accurate. You need 2 centimeter accuracy at least. So we worked very hard, and this was actually a problem we realized after the qualification, after the practice tournament. So we had to build something entirely new for this, and we put an enormous Kalman filter over this, and here is the result. And the white lines are still in here, but they are so small that they're not even visible. And we have a very stable input in our world. The world state is what we call the positions of the robot and the velocities and the angles, etc. And it's extremely stable, and we have some very good experiences with it already. Well, the circle is full again. I've been talking about robots, computer, and the camera. But with a full circle, I can't leave this place without showing how everything is interconnected. So today we would like to show our robots in real life, in real time, right in front of your nose. And we are very nervous about this. So let's give a go for our team members, which are now putting the robots on the stage. Let's add some light in here. We really need stable light, and we might need to recalibrate something. Please don't use flash on your smartphone when doing making pictures. And we are going to see our new robot in action. And we have our first And in the meantime, I would like to have 2 volunteers from the audience. Is there someone who's willing? Yes. You can come up here to me. And another one, please. Yes. Please come forward.
Because why just only have robots play against each other if you can also play against our robots?
We will have some team members walking around the field sometimes to put the ball back in. Just next to the corner. So Rob is currently instructing some people to teach them how to drive robots with a joystick. This is kind of a penalty situation. So we have 2 people from the audience here, and they will soon drive with the blue robots. The blue robots are not controlled by the computer, but the yellow robots are fully controlled by the computer. And soon you will also see the interface of RoboTeam AI on the screen. There it is. The green line you can see there are the paths we calculate, and we try to follow these paths. The yellow line you see is when the robot has calculated to make a shot, and that's the shot she tries to make. So what you currently see happening is that we lost one of our robots in vision. If we lose the robot in vision, we stop sending commands to it. So we have to recalibrate to get the colors and the caps. We have to calibrate them exactly right. Oh, yeah, there it is. So in the interface you can see that our yellow robot is called D1, which means defender number 1. It's currently defending. It's I think it's very scared of you guys. So our defenders position themselves always between the ball and the goal. Or if already one of the defenders is doing that, it positions itself between other robots. So it tries to intercept passes. When it has the ball, it will kick the ball forward. And for this demo, we program it to immediately shoot at the goal. And in that case, the robots will show no mercy against the people here with the joystick. In the interface you can see the orange dot is the ball. Sometimes it would show an orange line. The orange line is actually the position, the end of this orange line is the position where we expect that the ball will eventually lay still. We use this to calculate where to catch the ball would we need. Come on. You have to defend it. Very good. Yeah. Yeah, we have some activity at the computer's goal there. It's artificial. Yes. I think that was quite some nice game already. Is it back? Yes, it's back. Yes. Yes, I think it was a proper goal. Okay, yeah, I would like to thank the people from the audience. You have been there. I think it was a test to see if you could join us to the RoboCup instead, but I guess we go with our new system instead. So I would like to give the word back to Rob. Let's see if we have our presentation back on again. Oh, I'm a very nice ball, by the way. Because
For some reason, this
yeah,
is
we really choose our team color in a bad way. It looks too much like orange. Rob, here's your ticket. Thank you.
Yeah, so those are robots and those are in action, and I hope they'll be just as good when we go to Sydney. But of course, we could have not done this alone without our whole team, so I would like to really invite them here with me. Not done this without all of us, but also not without all the company sponsors, just people interested in helping us out to build the robot that we have right here. Thank you all for coming, thank you for listening to us. We will be having a drink right after this here in the foyer. We will each give you a coin when you walk out, so for a drink. So please do make sure to grab that, because otherwise you'll be very sad. Thank you for coming.